Welcome to recording on pages 3 and 4 of the section 3.5 notes. Here we're going to discuss how we came about for the derivative of sine x analytically, as likewise for cosine x. Before we get into doing the formal definition of the derivative on sine x as well as cosine x, let's talk about some limits that we should know. So we do know that the limit of sine x over x is 1 when x is approaching 0. We've talked about that back in section 2.1. If you simply replace x with a different letter like h, it's, using a different letter is totally arbitrary, it doesn't matter. That's still going to be 1 over here as well. This is a new one. We haven't done cosine h minus 1 over h. If you were to actually graph that in your calculator, or if you were to plug in like a number close to 0 in your calculator, like cosine of like 0.1 minus 1 over 0.1, you're going to get, so let me actually graph that in my calculator so I can see how it looks. Let me switch to, hold on, my calculator's really slow right now. Let me switch to Radian mode here, and yeah, so this is going to be y equals cosine x minus 1 over x. Looks like that. And there's actually going to be a hole right there. So that limit's going to be 0. So that's a new one. And we usually just use graphical or numerical means to evaluate that. So anyway, keeping those two limits in mind. And by the way, when we do trig derivatives, we have to assume Radian mode. So if you're doing like the end deriv feature in your calculator and you have a trig expression that you're taking a derivative of, you have to be in Radian mode. Otherwise, it's going to give you a different answer if you're in degree mode. So the assumption is that the derivatives of trig functions, they assume Radian mode. There's a formal way of explaining why that's true. We're not going to get into that here. I think we do that sometime down the road in this class. I can't remember when. We do that more formal proof. But for now, just realize that you have to use radians when doing the trig derivatives. Graphically, we are using radians when we look at what's happening here, when we evaluate a sine x over x graphically, or the limit of cosine x minus 1 over x. And we were in radian mode, so that might kind of help you to realize you got to be in radian mode when doing trig derivatives. Now, derivative of sine x. If I do the formal definition, now remember, we had an identity from pre-calculus where you have sine of a plus b is this. I know identities were kind of a sticky issue for some people in pre-calculus. That could be one of the pain points, but we don't really do too much with identities, and I don't expect you to memorize them or do formal verifications of identities. So don't worry about that, but we're going to use that to our advantage when we do derivations of derivatives. So I have the limit as h approaches 0, and that's going to be sine x times cosine h plus cosine x times sine h minus sine x all over h. Now we're going to have to get a little creative with the algebra here. I'm going to break apart this fraction. I'm going to break apart in this manner. Sine x times cosine h minus sine x over h plus the limit as h approaches 0 of cosine x times sine h over h. So essentially what I did was I kind of combined these two to be in one fraction, and I combined this one to be in another fraction. Remember, if you have like 1 plus 4 minus like say 7 over 2, I could totally write this as 1 minus 7 over 2 plus 4 over 2. There's no reason why I can't do that, because if I bring them back together, I get back to my original fraction, right? So I totally could do what I just did. Just being creative with my fractions, right? Not breaking any rules here. Now I'm going to factor out sine x from the first fraction, so I have cosine h minus 1 over h, limit as h approaches 0. And here, I'm just going to break it apart like this. Limit as h approaches 0 of cos x or actually, let me rewrite that. I'm going to pull cosine x to the left because it doesn't have h involved. So that's totally a legitimate thing that I'm just doing right now, that you could totally get away with that. It's kind of like a constant in a way, because it doesn't have h in it, and limits obviously involving h. Now here, I know that this limit is 0, and again, I could pull that sine x off to the left here, and I'm taking the limit as h approaches 0 of cos h minus 1 over h. And here, that's just going to be cos x times 1, because this limit here equals 1. Well, the limit as h approaches 0 cosine h minus 1 over h we just discussed, we kind of, if we looked at graphically, is 0. So what this tells me is that this part goes away. Okay, I've run out of space, so sorry about that. So I'll just have to squeeze it down below. So that's going to be, need a good drawing feature back up, sine x times 0 plus cos x. So derivative is just cos x. Graphically, that makes sense too, though, because I mean, if you were to graph sine x, and we see that at the peaks or low points, the derivative there is 0, which is at pi over 2 and 3 pi over 2. Cosine is 0 at pi over 2 and 3 pi over 2. We also see that sine is rising from 0 to pi over 2, and cosine is positive in that interval. And then we see that the tangent lines are negative from pi over 2 to pi, and cosine is negative in that interval. So you can kind of use tangent lines from a sine graph to get the graph of cosine x. And that's why cosine is also the derivative of sine graphically. But analytically, we see right here for sure. And numerically, you could always, take a look at like different secant lines, I guess. If you were to take like different points on a sine graph and like try to find the slope of the secant line between 2 points that are really close together, and that could be like the value of the cosine there as well, the slope that you get. Then for this one, we'll do something very similar, and that's the identity for a cosine of a plus b. So we're going to use that to our advantage. Again, don't worry about verifying identities. We don't do that in this class. You don't have to memorize identities either. The AP doesn't require you to do that as well. But you get cosine x times cos h minus sine x times sine h minus cos x all over h. And then again, we have to get a tad bit creative here. So I'm going to break apart fractions in this manner. Cosine x times cosine h minus cos x all over h. And then I'm going to do minus the limit as h approaches 0 of sine x times sine h all over h. Now, similar to what we did in the previous example, we're going to factor out cosine x here. You have that. Minus the limit as h approaches 0. And actually, I'm going to pull the sine x off to the left here. Times limit as h approaches 0 of hold on a sec here. That's times, my bad. Sine h over h. So I know that this is 1. And I know this limit is going to be 0. So basically, this kind of just goes away, leaving with just negative sine x. And that's how you get the derivative of cosine. Derivative of cosine is negative sine x. Now, if you look at the graph of cosine, we have horizontal tangents here and here at 0 and pi and 2 pi. Well, that's where sine is 0. At 0, pi, 2 pi, every integer multiple of pi. We also have cosine is dropping over here in that interval. But because it's negative sine x, the double negatives kind of cancel out. So we expect sine to be positive in the first quadrant from 0 to pi over 2. And then, of course, we see the derivatives are positive for cosine, but because of negative sine x, that makes it negative. And we do know that sine is negative after you hit pi. From pi to 2 pi, sine is holding negative values. So again, we see graphically what's happening. And again, numerically, if you were to find 2 points on a cosine graph and did a secant line between them and saw what that slope was, that would be essentially the sine value but as a negative. So that's what's happening there. And lastly, make sure you know your unit circle really well. This I actually am not going to be terribly flexible. You have to really know this because we're just going to be doing a lot of science stuff and like evaluating like slopes of tangent lines and finding equations of tangent lines, all that stuff. We're going to do a lot of trig derivatives and anti-derivatives. That's what we do in the second semester. So like sine 0 is 0. That's 1. That's 0. Here that's going to be 1, 0, and undefined. Here, make sure you know it's 1/2, root 2 over 2, and root 3 over 2. Here it's the other way around, root 3 over 2, root 2 over 2, and 1/2. Here, remember, tangent sine over cosine, so it's 1 over root 3. Or some people like to rationalize and say root 3 over 3. I don't really care if you rationalize. The AP doesn't care either. That's 1, and that's just going to be root 3. So make sure you're comfortable with that. I remember unit circle. It's one of my favorite things to teach when I taught altitude trig honors and pre-calculus. And I've taught pre-cal regular and pre-cal AB honors. Some people have a hard time with it. Maybe just if it's not taught well, or if we're not really full engaged in the material, it can be tough. But hopefully you guys are comfortable with unit circle. And if you're not, let me know. I'm more than happy to kind of give you a little explanation of how it works and make you hopefully more comfortable with it. All right, so that ends the second half of the 3.5 notes, pages 3 and 4.